In the last unit, we systematically derived algorithms for computing the dot product, and on the left is the result of that, namely the algorithm that corresponds to loop invariant number 1, which we then call variant number 1. The big question now becomes, how do we take this algorithm and how do we translate it into code? Obviously, if we translate this into code using loop indices, etc., then we haven't really gotten any further because there's still a lot of opportunity for introducing errors in that translation. What we need to do is we need to program in a way such that the code is a direct translation of the algorithm as represented here. And for that, what we did is we created what is called an application programming interface that allows the code to reflect the algorithm. What do we have on the right here? We have a live script in which we describe that we want to implement the dot product, and here in the first code box we set the path just in case the path wasn't set correctly. Then in the next code box we set the vector to be of length 4. We create 2 random vectors that are integer valued of length m, 4 in this case, and then we create an alpha that we set to 3, and then here we call a routine that we're about to implement, and then down here we check whether it actually gave the correct answer. And the function that we're going to implement, we're going to have to place in this final box right here, because at the moment in live scripts the functions always need to come at the end. So how do we go about that? Well, over here is a link to the Spark web page. And when we click on that, we get this right here. And notice that conveniently it has remembered from the last time that we implemented the dot product. And it may be that this for you actually is variant number 2. One thing that we're going to want to do is put a capital S here because we named our function with a capital S. And then in theory, we should be able to just change to wanting the FlameMatlab, that's the Flame API based implementation of the algorithm, and everything should show up on the right. Unfortunately, there seems to be a bug in the code that runs the Spark web page, and therefore we're going to have to reset it if it doesn't automatically show, and that you do by saying reset form, and then you go up here and you say reload the web page, and for me that tends to fix things in that order, by the way. So then you have to start over, put in sep dot unblocked variant number 1, 3 operands, x vector top to bottom input, y vector top to bottom input, a for alpha, scalar, no partitioning input and output, and the output language should be FlameMatlab, which, as I said, is the API for MATLAB for implementing Flame algorithms. Okay, and if we now put this right next to the algorithm, hopefully things are very obvious. Hopefully they are direct translations. What do we have? We have a partitioning of x and y. We have a partitioning of x and y, where in goes the vector x, out comes a top and a bottom part to x. Same thing for y. Okay, we have a m of the size of xt is less than the size of x. Notice that it's the row size. So in MATLAB, size extracts the row and column size of a matrix. We want the row size, so we indicate that it's size of xt comma 1, etc. Okay, and hopefully just by looking on the left and looking on the right, you get it, you understand. Okay, the FLA bottom here says that one element is to be partitioned from the bottom part, so that would be the top element of the bottom part. The result of that is then stored in chi1, with the rest of the bottom being returned as vector x2, etc. Hopefully this is straightforward. Then you go and you copy and paste all of this into this box down here. So what's left to do? Well, notice that we need to go here and we need to say alpha is equal to chi1 times psi1 plus alpha with a semicolon there, otherwise it gets printed out every time. That's just a translation of what we have over here. And now let's save this. Okay, so here at the top we print out what the result is of calling the function. It might be good to also print out what MATLAB would compute. So let's say, okay, let's also print out x transpose times y plus alpha. And now let's execute and see if we get the right answer the first time. Drum roll. On the right here, the answers will appear. We execute it. Notice that what this here says is x is some random vector, y is some random vector, alpha was taken to be 3. It is 5 that is computed by our function, and then it's 5 that actually is the answer computed by MATLAB, and indeed the same answer is returned. So, all is well, and we got the right answer the first time. So now what I want you to do is do exactly the same thing, but for loop invariant 2, which gave you algorithmic variant 2.